For today's video, we're going to talk more about those covalently bonded molecules, or sometimes called molecular compounds, and we're going to get into the concept of moles. Okay, so to sneak up on the mole concept a little bit, go with me on a little bit of a thought experiment. Let's consider lithium. So this is atomic number 3. Look at your periodic table. Now, yours could easily have a different number of significant figures than I'm going to use here, but that's kind of inconsequential. The idea stays the same. So the mass of lithium in Daltons, and remember this is our unit that we're using, DA, Daltons, or you could say AMUs, atomic mass units. You might have heard that in the high school version somewhere before. But that's okay. Those are fairly interchangeable as far as you're concerned here in general chemistry. So from the periodic table, what's the mass of lithium in Daltons? And looking at my periodic table, I see 6.941 Daltons is the mass of a single average, on average, the mass of a single lithium atom. So my thought experiment here is, well, Daltons are really tiny, but there should exist some number of lithium atoms that if you had them all in a block, they would equal a mass in grams numerically equal to, I should say, that same number that you had mass of Daltons. So if I'm looking at 6.941 Daltons for the mass of a single lithium atom, there should be some number of lithium atoms that would give me 6.941 grams of lithium. So hold that in your head for a second, and let's think about aluminum. Similarly, aluminum on the table, now mine has a lot of decimal places, 26.98154 Daltons. So on average, a single aluminum atom has a mass of 26.98154 Daltons, or AMUs. Okay, but again, there should be some number of atoms of aluminum that if you had them in a chunk, they would be 26.98154 grams. Well, there is such a number, and it turns out that this number of lithium atoms that would give us that in grams and this number of aluminum atoms that would give us that in grams is the same number. In fact, it turns out that it is the same number that will do that for every element out there. This is the number. So 6.022, I'll usually round it off that far, but you can look it up and have more decimal places if needed for the significant figures that you're working with in a problem. But 6.022 times 10 to the 23rd. Now, technically this needs a unit. So it is 6.022 times 10 to the 23rd things per mole. And I will use this tried and true example, just like saying there are 12 eggs per dozen eggs, or 12 eggs or 12 donuts per dozen donuts. There are 12 things per any dozen. Well, the same thing applies here. There are 6.022 times 10 to the 23rd. It's a very large number. Things per mole is what this means. So now working backwards should be easy here, right? So if I take this is that same number, 6.022 times 10 to the 23rd atoms of aluminum would have what mass in grams? Well, that's that special number. Avogadro's number is what it's called. So that number of aluminums would have a mass in grams equal to the mass listed for aluminum on the periodic table, 26.98154 grams. That's a really difficult number to write over and over and over again. So we turn it into a unit. Just like you don't want to write, you don't want to check out 12 eggs every time you run through a cash register, or 12 donuts every time you buy a box of donuts. You sell them in dozens, right? So we usually talk about, in chemistry, how many moles of things we have. Instead of writing this number over and over again, we just say, well, it's a mole. This is 1 mole of aluminum atoms, or you could have a mole of whatever different things. So we always just use a mole of things. So it is representative of that number. Mole of anything is that number of things. And we can take it and run, of course, we're going to run calculations with it, right? So think about this. So let's think about a mole of water. Now, I've pulled up my periodic table again, and I'm looking at it, and I'm thinking a mole of water molecules. Now, each water molecule, let me look at a water molecule here. So a water molecule has H2, 2 hydrogens, and 1 oxygen. All right, so if I've got a mole of that, right, then a mole of oxygen atoms, well, let's see, looking on the table, my table has got 15.9994. So that is, if I've got 1 mole, 1 times 15.9994. I'm going to do the units right here. Grams per mole. But then look here, I've got this 2, right? So I've got 2 1.00794 grams per mole. And I hope you can see what I'm doing, color coding the different parts here. I'm going to add those together. I'm going to grab my calculator out. You should do the same. You should calculate with me on all of these. 15.9994 plus 2 times 1.00794. And I get 18.01. Let's see. I can only go to the 4th decimal place. Addition. Remember your addition rules on your sig figs. So 5.3 grams per mole. And to be honest, most of the time when I talk about the molar mass of water, I'll say about 18-ish grams per mole. So if it is 18 grams per mole and we have precisely 1 mole of water, then we have 18 grams of water. So by the time you see this video, we will likely have talked about covalent bonds a bit while working on stuff in class. But I want to be a little more explicit with them here. And they'll come back again later after we've laid some foundation and cycled back around to them again as well. So consider hydrogen and fluorine. And we're going to make a bond from the 2. Now, in this case, hydrogen's got that 1 electron. We can call it a valence electron, but hydrogen just has 1 electron, period. And fluorine, now here I am only considering what we're calling the valence electrons. Let me be specific about what I mean here. In the case of fluorine, and in the case of all of the period 2 and period 3 elements, we are going to say that the outer shell of electrons, and it usually wants to have 8 in it, is going to be our valence electrons. Now, when we talk about electron configurations, you'll see why I'm stopping talking about that clearly at argon. You can still consider stuff further down the table in the groups like iodine. You can still consider it to have 7 valence electrons. It's going to be a little more complicated. We'll get to that more in depth when we try to hang all of those huge number of electrons on things and try to figure out where they all go. But for right now, now fluorine itself, it comes with 9 electrons, right? But 2 of those, remember the first 2 are in a really, really close inner shell. And they don't really interact with anything because you've got a full inner shell surrounded by a larger outer shell. And only that outer shell is actually involved in bonding. And so we call this the valence set of electrons. Well, let's see. Fluorine's got 9. It's got 2 in the inner. That leaves 7 out here in this second shell, where there could be as many as 8. Now, fluorine is an extremely electronegative atom. Hydrogen is not. Hydrogen is middling at best. Down here, I have a contrasting scenario where I've got 2 different hydrogen atoms. And again, that hydrogen has its 1 electron. We can call it a valence. And so does this other hydrogen. Now, in the case of the hydrogen fluorine, the hydrogen is actually going to lose its electron. I'm trying to white it out there. It loses that electron. The electron goes over to fluorine to complete its octet. So we said there was really a lot of energy benefit to completely filling that shell. So here we've done so. Now, this is going to have a 1- charge on it, and it's going to leave this hydrogen with a 1+ charge on it. And they're going to be bound to each other by an ionic bond. And I realize, and some of you chemistry majors will see later, that this concept of a bond, when you're talking ionic, gets a little slippery. But for simplicity's sake, we're just going to call it an ionic bond between the hydrogen and the fluoride here, HF. But down here now, let's see, the fluorine was so strong electronegatively that it just stole hydrogen's electron. But now down here, is this hydrogen on the left stronger, or is this hydrogen on the right stronger? Well, neither one. What happens is each of them decides to just share. And so they make this one big, happy electron region in between them of the 2 shared electrons, one from each hydrogen. And we call that a covalent bond. I'm writing with a mouse, of course, so it's not beautiful. So that's the big difference. Up here in the ionic bond, this hydrogen has lost its electron. It ain't coming back. Down here, each hydrogen is sharing its electron so that both hydrogens get to act like they've got a full 2 electrons in their 1s shell, and neither of them has to lose it completely. So molecular compounds are covalently bonded compounds. They result when you have that sharing situation. And they exist as discrete. That means you could actually localize one individual, let's say H2 molecule that we made on the previous slide. You could find one discrete H2 molecule. Neutral. Yes, the H2 is neutral, and a lot of them when we're calling them molecules, we're kind of defining them as neutral. But there can be covalently bonded ions as well. But now it is usually, if you think back to that previous lecture, where they are on the table, it's usually a combination of non-metals. Has to do with, later in the course, we'll talk about the electronegativity of those metals and how they are quite close to each other. They often exist as gases, low boiling point liquids, and low melting point solids. And I added to that it also happens to be almost all of organic chemistry when you get to that course later on. So how do we name these things? Okay, so for ionics, we're kind of locked in a lot of ways, right? So if I talk about calcium chloride, that's an ionic compound. You know that calcium is going to have a 2+, that chloride is going to have a 1-. They're going to have to combine in a ratio of 1 Ca to 2 Cls, and so it's going to have a formula CaCl2. Cool. But now covalent, there's a lot more degrees of freedom here. We could do lots of things. Consider for a second carbon and oxygen. Now, with carbon and oxygen covalently bonded together, you are already likely familiar with both carbon dioxide and carbon monoxide. Those are both covalently bonded carbon-oxygen molecules, but they have different numbers, in this case, different numbers of oxygen in them. So we're going to talk about how that naming works. So the way your book says it is a more metallic element. I tend to say the less electronegative element. That's mostly the same thing, but to the left and bottom, those usually come first. Then the other name. And it does usually get the IDE number as if it were being a negatively charged ion. I would have probably done it differently, but they didn't ask me. So now here's the thing. So monoxide and dioxide, those are number prefixes on it. Mono meaning 1, di meaning 2. They're from Greek, and that's how, with covalently bonded molecules, how we specify how many of these different bits are in each one, how many different atoms are in each molecule. So here is a list of at least the first 10. I mean, there are prefixes for beyond this. I don't think we'll have to worry about them. If we do, definitely you should ask. Say, you said write down 10. I wrote down 10. I don't have 12. So that's fine. I would probably give you that. But you can memorize these. One of the things that has helped people before is you've probably seen in geometry, a pentagon has 5 sides, a hexagon has 6 sides. Those are the same root prefixes that give you these at least from 5 down. You might have to work a little bit on the first 4. But to be honest, I would like for you to just have those on your cheat sheet so that they don't get confusing later. Some little things that happen usually, so you don't say monocarbon dioxide. Usually for the first atom, if it's a mono, you just don't even say it. You just leave it off and say carbon, and then do use the di with the oxide part of it. Then there's a bit here about double A's. I don't know. That has to do with apparently how you like to spell things in English, which has never been a strong suit of mine. And then here are some examples of it. Maybe the examples help to clarify the rules. But you can see how there's no mono in the sulfur. It's just sulfur dioxide, right? But now if it's not mono, like here, dinitrogen tetroxide, N2O4, you would need the di. You can't just leave it off because it's not a 1. Oh, and I would not put these on a cheat sheet because it's unlikely. There are so many thousands and thousands of these. It is unlikely that you're going to write the right ones down on a cheat sheet. The other big naming thing that's going to come up is acids. We're going to spend a little bit of time later in the course on acids, and then in Chem 2 in 1212 we spend a lot of time. It's like a quarter of the course that we spend on acids. But in this course, we'll spend a little bit of time on the acids, and there's a plethora of different names. And so one thing I want to point out is that as far as you're concerned for general chemistry, this H plus coming off in water is the key. That's why we're going to call things an acid. There are other more complex definitions of acids that we'll get to, especially in orgo. But for right now, anything that can donate that H plus ion to water in an aqueous solution, that's what we care about, and we're going to call them an acid. So if you look at all of these, there's that H hanging off the front of it. Sometimes there's more than one. That's going to get complicated. And here, if you look at acetic acid here, we will tend to write things in different ways, but sometimes you can see, look at the way this is written. You've got an H and then C2H3O2. Well, look at those H's are different, and they are quite different the way they're bonded. So these H3s are written in a different place than this leading H, and that's a good indicator. Oh, that's going to act as an acid. This H plus on the front, this H on the front is the one that's going to come off in solution, causing acetic acid to be an acid. These H3 here, they're bonded to one of the carbons, and they don't come off very easily at all. Some of these will come off sometimes with something like H2CO3. You can get both to come off. Sulfuric acid, you can definitely get both to come off pretty easily. Biology, phosphoric acid, like I mentioned last time with those phosphates, well, you can make an acid out of your phosphates with 3 different H's on it. All 3 of those can come off under different conditions, and this is one of our keys to how life works in biology is this phosphoric acid, or having just 2 H's on it, that's monobasic, or having two fall off and have 1 left on, that's dibasic, and you can have all 3 of them fall off and call it tribasic. It gets pretty complicated, but the biology folks love working with the phosphoric acid system. All right, our 2 big classes of acids that we're going to worry about are binary, or sometimes these are called elemental acids, because basically they are a combination of 2 different elements, hydrogen being one of them, in like this down here, hydrogen and fluorine, or hydrogen and chlorine, or hydrogen and bromine. Those make simple binary acids. So you will change the suffix to "ic", so instead of hydrogen fluoride, that's a gas, you would change it when it's in aqueous. This AQ means in aqueous solution. We'll talk more about that later. So in aqueous solution, we'll call that, instead of hydrogen fluoride, we'll call it hydrofluoric acid. Hydrofluoric acid. Hydrochloric acid is very common. Some of these others. Be careful with this last one, hydrosulfuric acid. Hydrosulfuric acid is a different thing than sulfuric acid. That's going to be on the next slide. Okay, so just make sure that you get this naming convention down. So you kind of, I don't intend to like quiz you on this, but it'll be buried in problems a lot of times. Like just react hydrochloric acid with something and tell me what it produces. Well, I guess to do that, you have to be able to know what hydrochloric acid means in the first place to get the predicted product right. The other big class of acids that we're going to care about here are called oxy acids. So they have oxygens bonded in a very specific way. We don't talk about the hydrogen. You know it has hydrogen because it's an acid. But you just start with the root name of the ion. Now, whether it's ate, ic, ite, us, that depends on how many oxygens, and it depends on the redox state. And I know we have not talked about redox yet. We will later in the semester, but it has to do with that. So for now, on the oxyacids, you probably are going to want to write those down on a cheat sheet. And let's see, I think coming up here, yeah, here's a good list of. I think this is going to get most of them. So you probably just want to put these on your cheat sheet as well. And some of them, stuff like acetic acid, there's no great reason why this is an acetate ion. It's just an old name, and so that's what we call it. Now, in this case, this one does follow better rules. So, because you can have, obviously, right here, these two together, you can have an NO3 or you can have an NO2. And what that's going to be is, it's about the redox state of the nitrogen. But this one, you have to kind of already know, I guess, that NO3 is as far as you can go with that system, and so you put the ATE on the one that goes as far as it can. So in this case, it's 3. So that is nitrate, NO3, and so nitric acid. But in this case, NO2 is not as far, so it gets the OUS ending. So HNO2 is nitrous acid instead of nitric. Let's see, similarly, sulfate. And in this case, the sulfur can have 4 oxygens maximum. And so it gets the ATE, and it is sulfuric acid. This is kind of you would see in a lot of wet batteries. But SO3 is 1 oxygen less than all the way, so it gets the OUS, so sulfurous acid. Phosphoric acid, like I said, that's the common one you'll see in biological systems. Okay, and I'm pretty sure that we worked some problems already with empirical formulas. I just wanted to put a slide in because I couldn't find one, just to be explicit about everything. So a molecular formula tells you how many of the things are actually all in there in that discrete molecule. For instance, benzene is C6H6. So the molecule benzene, it actually does make a hexagon of carbons with a hydrogen sticking off each one of those carbons, and then everything all bonded together in there. I can draw that for you if you would like. But there are 6 carbons and 6 hydrogens in there. Now, if you boil those down in an ICP, which we do have in the lab, I can show you that, you'll see a mass of carbons and you'll see a mass of hydrogens. Well, when you work it out with the molar ratios, you'll see that there's 1 carbon for every 1 hydrogen. And that works with this ratio here. Acetic acid, if you work on the molar ratio of it, you'll see that it is 2 hydrogens and 1 oxygen to every carbon. But it could be a little misleading because that's only the empirical formula. The actual molecular formula over here is C2H4O2, or as we wrote it a while ago, HCH3COO. Or I think maybe it was HC2H3O2. You see that all those are the same thing. But when I'm writing it this way, I'm kind of tipping my hand that, oh, look here, we got an H hanging out front. That one's going to fall off and make this an acid. Okay, and so for next time, next time will be solution concentration. So we're finally going to get into when we talk about how concentrated a solution is next time. So I think probably you've read most of this now, and we're going to get into here molarity and other units of solution concentrations. So all of chapter 3 for next time, and when we get to this.